procedure here. You can see there's 16 pages. This thing is. It's not amazingly long, but there's a lot of pictures, and we're going to go through this thing. The things that we'll need are the 2.3 meter track system. I mentioned it was 2.7 meters. That's this guy. We're going to need a collision cart. That's what they call this magnetic guy. A fan assembly, sure thing. A motion sensor, version 2, got one of those. The Model 500 interface, and then we have 3 files that we're going to be using, and the software we're using is called Data Studio. And of course the company, because you can see it here, the company that makes all of these things so we can study this is called Pasco. It's just a Pasco company. Fantastic. I think I've printed this thing on both sides to save paper here. Here we go. What do we want to do? We wish to go look at file number physics number 1. So here we go. So we're going to see back here. Let's see what we can do. So I'm going to go ahead over here and fire up the computer. And I'm going to open up Data Studio and see if it works. Hopefully it works. It does. Wonderful. I close this, and I want to go to the experiment, and I want to change the interface to make sure that we're using the Science Workshop 500, which is this dude right there. And then I say OK, and it found it, and it is initializing it. Hooray! And it is 3, 2, 1. Fantastic. There it is. It's ready to roll. Ready to roll. It just turns out rather than assembling and telling it what it's plugged into it, we're going to use that later in the semester. We're going to use a file that's already ready to go. So what I'm going to do is I'm going to open an activity. It's called that. I'm going to go to this PC. I'm going to go to the hard drive here, and going to go to ISBT 2020 ISBT112. That's us. And going to go to physics experiment number 1 because this is the first physics experiment, and open this puppy. And there we go. We're going to use the motion sensor to observe the relationship between the motion of an object, of a graph, and its position and time. Fantastic. I'm going to minimize this little sheet here, and this is our dude. Wonderful. And then I also want to, if it's not here, this guy was last saved, someone had closed it. I'm going to take this match score here, I'm going to drag it down to this window display, and we'll be looking at this later on. And just for now, I just want to introduce this thing. Here is the score. I'll show in a second what that means. Okay. So what we have here, and if I go over here and take a look at this thing, okay, mount the motion sensor at the end of the night. We did that. Position the cart in front of the motion sensor. It is ready to roll. We did that. Okay, we're moving it back. Here we go. Enlarge the graph display until it fills the monitor screen. We've done that. That's pretty big. Wonderful. Study the plot of the position versus time in order to determine the following. Okay, so here's the plot. Here's another copy of it. We're going to use the screen over here. How close should the cart be to the motion sensor at the start in meters? Okay, so over here, here is our chart. The chart already has a red graph. This red graph is how we should, or how I should, move the cart while this sensor is sensing. If I take a look at it, I have, reading the axes, I have time on the horizontal axis. Sometimes we call that the x-axis. It could be whatever you want, but it's definitely the time axis now. The vertical axis over here, we're not talking about up and down, because we're definitely moving side to side, is where it is in the vertical axis, but this is just in meters. It turns out the real motion is side to side horizontal, but on the graph it happens to be the vertical axis. So again, that's vertical in the lab, this is vertical in software, and this is horizontal in the lab. We're actually doing horizontal in the lab. So reading this, and this tells us something, the time is 0 through 10 seconds, okay, units of seconds. So it's asking here, where should it start? Well, I'm guessing it's going to start at 0. That's when we start our stopwatch. And if I go straight up along the vertical axis, which is meters, the distance axis, I'll see that it's at 0.4 meters. So that just tells us right away. And if you've been reading graphs since before you could walk, talk, or eat cereal, that's a pretty obvious thing to do. We're supposed to take this guy right here and move the front of this guy down to there and put him right there at 40 centimeters, or 0.4 meters. That's that guy. If I do that, and if this thing is working properly, I should get this thing starting at 0.4. Now what happens is, so I'm going to take my pencil here. Let me grab I said pencil. I've never used a pencil. I'm going to use pen here. This should be, how close should the cart be, the motion sensor to the cart? It should be 0.4 meters, all right? How far away should you move the cart? Well, let's see what happens. I'm going to move the cart following this pattern, and I'm going to go the whole way up to here. It looks like this guy is 1.1 meters, okay? How far away I should move it a total of 1.1 meters. And how long should the cart's motion last? Well, let's take it out. Here's 0 and here's 10. So you could say the experiment lasts 10 seconds, but it's only moving. It's only changing its position, which of course is how we define moving, between 2 seconds and 6 seconds. So that's 1, 2, 3, 4. Only 4 seconds. So only 4 seconds. So this is how we communicate to each other using our system of explaining motion using a graph. We define what the horizontal axis is. It is time, and we give it numbers. We define what the vertical axis is, and we give it units. In this case, it's meters, and we give it numbers. And then we go ahead and plot on there what actually happened. So this is a prediction of what we think will happen. I'm not turning on the fan. It's going to ask me to start this and then use my hand to move this around. Now, when I move this around, what's going to happen is it's going to look to see how close my actual position is to what it's supposed to be. It's going to measure the accuracy. I think that's right. How close is the actual data, the measurement, to the truth? Okay, this is where it's supposed to be. So if I'm able to move this cart exactly correctly, I should be able to be right on that red line. And if I subtract the difference, I should get a score of 0. It's like playing golf. This is the match score. If I'm completely off and I get a giant gap or a giant space between the what is real or what I've measured and what is supposed to be, I'll get a large number. So my goal is to keep that low, okay? So I've analyzed what this thing looks like. Here's my cart. Let me go ahead and try this once. Here's 0.4. I guess I'm going to wait for 1, 2, and then I'm supposed to move it the whole way out here to 1 point, this guy right here. But if you look at this, how I'm supposed to move it is just smooth and steady, just a single line right there. So I'm not supposed to speed up and then slow down, or go there and wait. I'm supposed to go there and wait by 6 seconds. But this guy looks to be a nice smooth motion because nothing's really changing. So I think that's how it's going to work. I put my pen back in my pocket, and I'm going to go ahead and grab this guy over here and put this at 0.4 again. And what's great about this is it gives me feedback. It's going to show me where things are at the same time. I'm going to grab my mouse, and I'm going to press the start button, and we're going to see if this works. Okay, so press the start button, and I believe this guy should start chirping. Again, it should sound like a, it'll be a lot faster than that. And I'll get a few seconds to go ahead and adjust this to 0.4, and then I'll have to move. So let me see how I can do this. Here we go. Oh, I feel the pressure. Nope, get a little closer. Okay, there it goes, there it goes, there it goes, there it goes. Here I go, here I go. Oh, I gotta speed up, speed up. Keep on going. And I gotta stop, I gotta come back. And then I gotta sort of get it close to where it needs to be. And fantastic. Oh, look at that. That was the best, well, so far today, because it was the first time I did it today. So it turns out that the computer chooses what colors to use, and unfortunately red is difficult. They showed off and said, hey, the last time we did it, we got a score of 2. I pretty much suck and got a score of 2.564. Okay, so maybe I get good at this. I don't know. Is this something I need to get good at in order to be a good human? I don't know. Again, I'm going to start it at 0.4. I'm going to press start again. Different color this time. Okay, and now I have to go a little bit faster this time. A little bit faster, 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 a little bit stop. Bring it back. Oh, look at that. I'm glad I was recording this because I think that's the best score I've ever gotten in all of the years I've ever been doing this. So apparently I don't have an anxiety performance problem. That's pretty cool. So yeah, this time around, my recorded position was blue, and I was asked to go ahead and move the cart. And then I went ahead and overshot it a little bit and came back, and my match score is 0.4. Again, I could do this over and over and over again. I don't wish to get a score of 0, but I'm not a robot. I'm a human. Could I make a robot and design a robot to get this to be 0? Yeah, hopefully pretty close. That's what robots do, especially if the robot's job is to move a welding arm and then go ahead and put a tack weld there and here and here and here. It better move pretty darn precisely and accurately, otherwise things aren't going to happen. Okay, so there we go. So we could do this over and over again. If we had you fine folks in the lab, we would have set this up. Every table that you see here would have one of these guys running. We'd have a bunch of folks in here. We wouldn't have to social distance, which is kind of a bummer that we have to. And then everybody would be trying to see their best score, and we'd have a competition. And of course, that's what humans do to see how well things go. Let's look at some of these answers back here. What's going on? What is the relationship between the motion of an object, the cart, and the graph, and the position of the time in the moving object? That's what we're sort of answering right now. So in the graph, what is the slope of the line of best fit in the middle section of your plot? Okay, so what they're asking us to do, as I mentioned before, this line in here really was kind of, well, not kind of, it's very, very regular. What I can do is I can select just that center part, and it's just like any other Windows program. I can click and drag, and I can select just the data inside here. And then I can go over here to fit, and I can put a linear fit in there, and I can get the slope. And the slope that I got in the graph, what is the slope of the line of best fit for the middle section of your plot? I'm staring at it here, and I see 0.178. So 0.178. It gives me an uncertainty, so I'll put it down, plus or minus 0.0013. That's not too bad. And the slope is rise over run, so meters over seconds. So that's meters per second, which isn't too bad. Fantastic. And of course, this is not a revelation. We're going to be talking about this. If you've had physics before, physicists like to call this relationship of this slope of rise, which is meters, over run, which is time, we call that guy velocity, or speed, but velocity is in meters per second. That's how fast it's moving. What is the description of the cart's motion? Example, constant speed for 2, followed by no motion for 3. Well, that's what we have here. We have no motion for 2, none for 2 seconds. That's how it worked. And then there was a constant motion at 0.178 meters per second for 1, 2, 3, 4. That's what I said before, for 4 seconds. And then it stops and no motion for 1, 2, 3, 4, another 4 seconds. Okay, so that's how we could describe what I did. And also, if someone were watching me do this, we could, and we were writing this down in the newspaper, like, hey, what was the process? The process, the person with the magic hand, they moved it, they kept it there for 2 seconds after the data started. They moved it at a constant velocity of 0.178 plus or minus 0.0013 for 4 seconds, and then they waited for 4 seconds, and then it stopped the program. Fantastic. What would be the physical meaning of a steeper slope of the graph? Well, here's the slope. If it was steeper, meaning a higher rise over run, meaning that there's more meters per second, that means that this ratio goes up, then that means it would be a higher velocity. Fantastic. What would be different about the motion if the slope were negative? Okay, well, here's positive. That's kind of crazy. What if it were negative? Well, if it were negative, that means that this value of meters would be getting lower and lower and lower as time was getting greater and greater. The rise over the run, we still call this the rise, but it would be a negative rise. All that means is that this number would be getting shorter and shorter and shorter. It just means that the motion would be coming back towards the sensor. So positive in this graph is motion away. Not moving at all is just staying put, and then moving back towards the sensor is going to be negative. So it would be moving back, if you will, back to the motion sensor. Fantastic. Wonderful. That worked out pretty well. That was our first one. Hey, this is pretty easy. We would like now to use number 2. So what I'm going to do is, we're finished here. I got all this data. I'm going to go here to File and go to Open a different activity. Should we save this? Nah, you don't need to save it. That's fine. Number 2. Here we go. We're going to open this guy. Okay. This guy used the motion sensor to understand the relationship between the motion of an object. Fantastic. We did that. Wonderful. This time around, the match score is up there. I don't need to grab it. I'm going to make this larger again. There's that guy. And here's my match score. Maybe I want to make this a little bit bigger so I can see the match score better. The match score is nothing until I go ahead and do it. Same deal. Okay, so let's take a look at this guy. Here we go. This is page 8. It's telling us, oh, by the way, set it up. Well, we already set it up, so we're good. That's page 8. All right. Enlarge the graph until it fills the monitor screen. We did that. Study the velocity versus time. Oh, whoa. What? I'm sorry. Velocity versus time, not position versus time. So if I look over here, the x-axis, I keep on saying the x-axis because that's what we put on the horizontal axis pretty often. I shouldn't do that. It's the time axis. The horizontal axis is time in seconds, but this time the vertical axis is in meters per second, which we just said was velocity. This is velocity, not position. So this is a velocity graph, okay? Study the velocity versus time plot in order to determine the following. Which direction, positive or negative, should you move the cart in the beginning? Well, we said before that a slope on the position versus time, or meters per second graph, if it's up, it's away, and if it's down, it's closer. So this is down. So let's say we're going to have to move closer initially. And this isn't stopping. This is velocity. It just means that we increase the speed closer, and then we keep on moving closer for a little short time, and then we slow. This is still negative, but now it's a positive. Oh my gosh, my brain's going to explode. This is a lot more complex. Maybe I can just go ahead and do it and see how it works. Which direction, positive or negative, should you move the cart at the beginning? It should move negative. So I'm going to put that down here, negative. What's the maximum speed, positive or negative? Well, that's the highest value. This guy up here is 0.2 positive and 0.2 negative. So it's 0.2, again, positive or negative. And our other guy over there was 1.6.